Okay. Hello. There's one more interesting question. Arrival rate of a telephone booth are in, arrival rate of calls on a telephone booth are in Poisson fashion with an average time of 9 minutes between two consecutive arrivals. The length of a phone call is assumed to be exponentially distributed. This problem clearly shows us that queue doesn't mean a physical queue. There can be invisible queues. The buffering of any system is also assumed to be an invisible queue. Okay. With an average time of 9 minutes between two consecutive arrivals, the length of a phone call is assumed to be exponentially distributed with mean 3 minutes. There are a set of questions. Okay. First thing is determine the probability that a person arriving at the booth will have to wait. Okay. Second one is find the average waiting length. What's the probability that an arrival will have to wait for more than 10 minutes before the phone is free? Now, for this D question, it is same to that one, that note kind of thing that I have discussed that I omitted. That is to determine the probability that the waiting time in the queue is greater than or equal to some value. Waiting time in the queue. Okay, greater than or equal to T lambda by mu in the Q and in the system that I have discussed, e power minus mu minus lambda T, that one, now that question. So I omitted. Again, it is out of the scope. What's the fraction of a day that the phone will be in use? That's one question. The telephone company will install a second booth when convinced that an arrival would expect to have wait at least 4 minutes for the phone as the last question. Okay. So coming to the first one, before going to the first one or to find anything, the first thing that we'll be needing is the traffic intensity. So what's been given here is arrival rate of a telephone booth is Poisson with an average time of 9 minutes is being given. Time is being given, guys. Okay. Average time of 9 minutes between two consecutive arrivals. Inter-arrival time is being given, guys. Okay. So, time between two consecutive arrivals is being given to be 9 minutes. Okay. Right. Now, how do I find arrival rate? You know that. Arrival rate. How do I find it? It is nothing but 1 by arrival time. Okay. So 1 by 9, which is equal to 0.11 as my lambda. Okay. Yeah. Now, service time is also being given. Service time is being given to be 3 minutes, guys. Each call is taking 3 minutes kind. So, service rate would be 1 by 3, which is equal to 0.33. Okay. 0.33. So, rho becomes lambda by mu, the arrival rate by service rate, 0.11 by 0.33. Its value turns out to be 0.3. Okay, now coming to the first question. That is, determine the probability that a person arriving at the booth will have to wait. Okay. The booth will wait, the person will wait if there is a queue, right? The probability that the server is busy. The probability that server is busy. Okay. Only then the person will, when the server is busy, the person will wait. Okay. So it is nothing but 1 minus P naught. This is equal to 1 minus lambda by mu. I'm sorry. 1 minus lambda by mu. Okay. P naught is 1 minus lambda by mu, no? So 1 minus 1 plus lambda by mu. This would be lambda by mu, which is nothing but 0.33. So the person will have to wait 0.33 minutes, right? Now coming to the second question, that is, Find the average waiting length. Okay. So waiting length will count for the queue only, not for the system. Average find the average waiting length. What is the probability that an arrival will have to wait? That's the third question. Okay. So average waiting length. Waiting length is nothing but length of the queue, LQ. This is equal to lambda square by mu into mu minus lambda. This turns out to be 0.166, guys. Average waiting length is nothing but length of the queue or average number of customers in the queue. Number of customers in queue. Okay. Yeah. Okay. Next, as I have said, C question I am omitting. That is the probability that the waiting time in the queue is greater than or equal to T is given by lambda by mu e power minus mu minus lambda into T. This is for the waiting time. This is for the waiting time in the queue. This is for the queue. For the system, there is no lambda by mu. It is E minus mu minus lambda into T. Okay, this is out of scope. We don't have this one. Okay. Okay. So directly I am coming to the E question. What's the probability that an arrival have to wait for more than 10 minutes before the phone is free? Okay. Yeah. So, yeah, this come under this formula. Now coming to E question, C and D. One is for the Q and one is for the system. Okay. Yeah. Coming to the E, fraction of the day the phone will be in use. Means what? The server is busy. The same as the first one. Fraction of day the phone will be in use. Phone will be in use is 1 minus P naught, which is equal to 0.33. And the F question is the required waiting time in the queue. That's that F question is the telephone company will install a second booth when it is convinced that the arrival rate would expect to wait at least 4 minutes for the phone. Okay, they'll install a second booth if the arrival rate is more than 4 minutes. Okay, so first let us assess what is the waiting time in the queue. WQ, which is lambda by mu into mu minus lambda, which turns out to be 4, guys. The new arrival rate would be the new arrival rate would be lambda is equal to 0.19 arrivals per minute. Okay. Increase of the arrival rate to justify a second booth would be 0.19 minus 0.11. 0.19 minus 0.11. Increase of arrival rate to justify second booth. To justify second booth would be 0.19 minus 0.11, which is equal to 0.08 customers per minute. Okay. These are the things we have asked. C and D can be omitted. They are out of the scope of the syllabus. There's one more interesting question. A self-servicing store employs one cashier at its counter. 9 customers arrive at an average of 5 minutes, while the cashier can serve 10 customers in 5 minutes. Assuming Poisson distribution for arrival rate, there are a set of questions which are obvious. Average number of customers in the system, customers in the queue, time customer spends in the system, time a customer waits before being served, probability that there is no customer. Okay, these are the things that are being there. Okay, the interesting thing is all about here finding the row part, guys. That's it. Once you find the row part clearly, then I think all the remaining things are obvious. Arrival rate, what he has given is arrival rate is given to be as a 9 customers per 5 minutes he has given. It's 1.8 customers per minute. Of course, 0.8 we don't count. We'll round it off to the highest or the lowest number. Okay. Similarly, service rate. See, while the cashier can serve 10 customers in 5 minutes. Mu is equal to 10 by 5. Both are in minutes only, so no conversions required. Customers per minute. Obviously, arrival rate is less than service rate. It is a steady state. Hence, I go with the remaining things. Rho is equal to lambda by mu. This is equal to 9 by 5 by 10 by 5, which is equal to 0.9. Okay. Now he has asked you average number of customers in the system. It is nothing but length of the system, guys, whose formula is lambda by mu minus lambda. Average number of customers in the queue. It is ls by lambda. Okay. Waiting time in the system is ls by lambda. That is also their waiting time the customer spends in the system. WS is nothing but ls by lambda. So 1 by mu minus lambda. And this one is LQ. Second one is LQ, which is lambda square by mu into mu minus lambda. We have seen the derivation in the previous video. Yeah, WQ would be LQ by lambda. So lambda by mu into mu minus lambda. Why I am stressing upon the derivation part is, guys, if you don't remember the formula, you may tend to get confused. This is 8.1 customers, guys. WS is a waiting time, right? So it is 5 minutes. This is customers. This is 4.5 minutes. This is also customers. Length gives you the customers. Waiting time gives you the time. Okay. This is how I will do it. I think it should not be a difficult one. Also, he has asked probability that there is no customer. It is nothing but this is 3, this is 4. Fifth one is the system is idle. Okay. System is idle is P naught. 1 minus lambda by mu. Okay. So accordingly, I'll calculate. 1 minus 0.9, which is 0.1. That's how I'll calculate. Yeah, I think for a infinite capacity single server, these problems are more than enough, guys. Do check them.